Hello, everyone. My name is Maddie Lee. I am a civil, environmental, and sustainability major with a minor in sustainability. For my project, I did sustainable design and construction using COB, and these are my three team members and our advisors. So to start with our needs statement, so we wanted to provide more research for non-conventional building materials, specifically looking at earthen materials, and so we found cob. Now you're asking, what is cob? Cob is an earthen material made from sand, clay, straw, and water all integrated together. The straw provides a tensile reinforcement similar to rebar, holding everything together so it doesn't fall apart. It's also known as a vernacular earth construction because these materials can be sourced locally, regionally. It doesn't need to be trekked miles and miles away, so it's more sustainable. Additionally, this has been used for over 10,000 years. So some of the oldest cob buildings around the world are like 10,000 years old. And in this picture is a picture of a cob Airbnb. So they are seen today and are highly coveted. This is booked out till 2026. So moving on, why should you be interested in COP? So there are benefits, as I've been saying, minimizing our carbon footprint in processing materials, transporting materials, and other things like that. Additionally, it's efficient at regulating heating and cooling passively because of the thick, large mass. It's also fire resistant and has a 2-hour fire rating, so this is pretty relevant in California. Additionally, it's DIY friendly, so we're hoping to encourage people to learn how to build it themselves with that proper code and regulation in hand. Additionally, as you saw in the previous picture, it does have a certain aesthetic and ambiance of a very like beautiful natural building. You can make arches that you probably couldn't do otherwise. However, there are barriers that we recognize. It is labor intensive. My team and I experienced this firsthand. Additionally, it's not normalized in the industry. It's hard to get a contractor who knows how to work with cob. And then most importantly, there is a lack of adopted research and codes. There is the Appendix AU in the International Residential Codes. However, this is pretty limited and fairly conservative and isn't fully known to everyone out there. But it is legal to build cob in California. So moving on. So to add to this research and to contribute to the cob research community, my team and I decided to perform a diagonal compression test on 2-foot by 2-foot walls. So this is a standard method, an ASTM E519. On the first two pictures, A and B, those are some referenced research that we looked into. And then the other two pictures, C and D, are ART cob tests. So as you can see here, there is a crack right down the middle, and this is what we were expecting and hoping for. This shows a shear crack, a shear failure. And so the goal of this is to simulate earthquake-induced stresses that create a shear failure. So here's our scope of work: the testing, the construction of the walls, the data analysis, and then as well as the design of a cob house and a life cycle and cost analysis. So this is how we got the cob walls into the machinery. It was quite a large feat of engineering on our part to innovate this way. The formwork was designed by my team member, and we worked together with our lab managers to come up with this mechanism and process. So we used a hydraulic car as well as the forklift to lift that large weight. As I said, you cannot lift it by yourself. And then moving on, we also performed a soil analysis, performing a sieve, grain size distribution, as well as a hydrometer analysis. So we could classify our soil. We also came up with a mix design to resemble a design that would be used in the field. So we had people from the Cobb Research Institute help teach us how to do that. And then finally, we tested. So here are our 6-inch walls. We did 2 different thicknesses, and these had the cracks as expected, and there are those peak loads. This was within our range of expected values as well. So we also did 12-inch walls, and they also performed as expected. The reason why we did 2 different thicknesses was to test the scalability of these walls. So if we double the thickness, would that double the shear capacity? All right, and moving on, as you can see, it did not. So these 6-inch walls had a greater stress capacity than the 12-inch walls, which is interesting because we were trying to see and try and draw some conclusions. Additionally, we performed compression tests because per code, our mix needed to be 80 psi strength, and we did surpass that. So that was good. We also performed moisture content tests for both of these, and they were within expected ranges of 1 to 3%. And here's comparing the moisture content to the strength. And then here is sort of our overall objective in why are we doing this test. So as you can see here, this is a diagram of the theory of rocking shear. So with this, the whole wall needs to stay together when a lateral force is being applied. So by making sure that these walls have a shear strength of a certain capacity, we're ensuring that the walls stay together when an earthquake is subjected. So here's our structural design by my team member. And you can see there are two 10-foot shear walls on each side. And then here's our cost analysis. As you can see right here, it is more cost efficient to have a non-conventional building material such as cob, with and without labor. Here's our life cycle analysis, and this is pretty interesting because it really emphasizes how much less CO2 emissions are emitted when using cob. All right, and just wanted to reiterate, this is the benefits of working with cob. It's sustainable, affordable, and it's just healthy housing. It's using our environment around us. And we hope that further research can be done, whether at Santa Clara or elsewhere. Here's some acknowledgements. We want to thank the Cobb Research Institute and our lab techs and technicians and our industry advisors. Thank you.